Hello, we'll be presenting our project on image colorization using a supervised CNN model. Throughout this presentation, we'll walk you through the motivation, model architecture, training process, and the results we achieved. We chose colorization for three main reasons. First, we can immediately see how well the model performs just by looking at the output images. Second, abundant high-quality public datasets allowed us to focus on model development rather than data collection. Finally, the model architecture is based on well-known CNN techniques, so it is both effective and easy to understand. Now, I'll explain the pre-processing steps for training our CNN-based colorization model. First, we resized all images to 128 by 128 pixels to ensure efficient training while maintaining a sufficient spatial detail. Second, grayscale images were formatted as 128 by 128 by 1, while color images remained in RGB format, with each pair serving as input-to-output examples for supervised learning. Third, we normalized pixel values to 0 to 1 range by dividing by 255 to match our sigmoid activation function. Through this preprocessing pipeline, we efficiently trained a CNN to predict RGB color images from grayscale input. Moving on to our overall CNN architecture. As shown on the left, our model takes a 128 by 128 grayscale image as input and produces an RGB color image of the same dimensions. The architecture is a unit-style encoder to decoder with skip connections using sigmoid activation and MAE loss function. The main components, summarized on the right, include convolution blocks with ReLU activation and batch normalization. The encoder uses max pooling for downsampling, while the decoder using convolution 2D transpose for upsampling. Skip connections preserve spatial features, which is key to UNet. The detailed structure of each encoder, bottleneck, and decoder will be explained in the following slides. This slide shows our model's encoder. A 128 by 128 grayscale image is input and passes through 4 convolution and max pool blocks. At each stage, the image is compressed to extract high-level features, ultimately producing an 8 by 8 feature map with 255 channels. Next is the bottleneck. The feature map from the encoder is input here, passing through the convolution block, which expands the channel count to 512 while maintaining the image size. This slide shows the decoder and output layer. The feature map from the bottleneck passes through 4 transpose convolution, concatenate, and convolution blocks, gradually expanding to the original image size. Skip connections are utilized here, combining feature maps from the encoder. Finally, a 1x1 convolutional layer and a sigmoid function output a 128 by 128, 3-channel color image. The paper we referenced is Colorful Image Colorization by Zhang et al. This study introduced 3 key techniques for generating colorful images: a classification-based approach, class rebalancing, and the use of a temperature parameter. Here are our actual implementation results. By applying skip connections to the encoder-to-decoder architecture, we preserved fine image details while improving color restoration performance. For performance evaluation, we used PSNR and SSIM metrics. PSNR measures image quality similarity between original and colorized images, while SSIM evaluates structural similarity and visual quality. These metrics enabled quantitative validation of our model. For training stability, we applied reduced LR on plateau and early stopping callbacks to flexibly adjust learning rates and prevent overfitting. Finally, by implementing a regression-based approach, we achieved effective training even with a limited dataset of 3,000 images. The results of the model are as follows. We can see that the model achieves quite high accuracy in colorizing images with strong cyan and blue tones. However, due to the limitations of the regression model, we can also observe that the representation of red-toned colors appears somewhat insufficient. Our image colorization model uses a UNet-based regression approach, which has some key differences from the classification method used in studies like Zhang's. Zhang's model classifies each pixel into one of 313 color categories, treating colorization as a classification problem. It uses a conventional CNN without skip connections, and its output is a probability distribution requiring post-processing. This method allows for diverse color expressions. In contrast, our model employs regression, directly predicting continuous A and B color values for each pixel. We use a unit architecture with skip connections. The output consists of continuous A and B values that can be directly converted to RGB, meaning it predicts a single fixed color per pixel. The primary reason for our choice of regression was the practical limitations of data and resources. Zhang's research requires a large-scale dataset of about 1.3 million images with pixel-wise labeling for 313 classes. With around 7,000 images and limited GPU environment, training a complex classification model was not feasible for us. Therefore, a regression model that directly predicts AV values was a more achievable option in our context, though this comes with some trade-offs in terms of color richness and rare hue recovery.
Now let's compare how the two models are trained, focusing on their loss functions. Zhang used cross-entropy loss as its classification problem and incorporated a technique called soft encoding. Soft encoding assigns each pixel's true A or B value to multiple nearby color bins, weighted by proximity, enabling the model to learn relationships between similar colors. They also applied class rebalancing, giving higher weights to rare colors to prevent the model from being biased towards common, dull tones. Our model, on the other hand, used MAE loss. This approach minimizes the average absolute difference between predicted and true A or B values. While stable, MAE treats all color error equally, which may cause the model to ignore subtle differences in saturated or rare colors. As a result, our model tends to make safe and conservative predictions, while Zhang's model is trained to be more bold and expressive. This time I'll share our attempt with the LIB color space-based model and the challenges we encountered. The original model took only grayscale images as input and directly predicted RGB images, which resulted in high complexity. To address this, the LIB color space-based model converts RGB images and uses only the L channel as input, while setting the A and B channels as prediction targets. The predicted AB channels are then combined with the input L channel and converted back to RGB. Although the LIB-based structure theoretically allows for isolated color prediction, issues such as color distortion occur due to difficulties in post-processing and scale adjustment. To address these problems, we tried methods such as AB channel clipping, normalization and value range adjustment, and changing the loss function, but none of these attempts produced meaningful improvements. In our second approach, we enhanced color processing by adding residual, attention, and color enhancement blocks to the existing model. In the output stage, we predict R, G, and B channels separately and then combine them, enabling precise color adjustment for each individual channel. For the loss function, we applied higher weighting to the red channel and introduced HSV-based loss to encourage color diversity and intensity. Next, let's take a look at the model's performance. Unlike the baseline, which only used dropout, our model combines dropout plus attention plus residual, aiming for more stability. Looking at the images on the left, we can see that overall the results are stable and the predictions are good. However, as you can see in the images on the right, the expression of red tones is still lacking. Through this colorization project, we successfully implemented a CNN model and confirmed the process of converting grayscale photos to color images. Although environmental constraints prevented us from fully implementing the original paper's methodology, we were able to understand the practical limitation of regression models and RGB channel approaches. This concludes our project presentation. Thank you.